When scientists finally declassified what happened after the US military exploded nuclear bombs in space, they discovered something terrifying. The radiation is still there, circling Earth like an invisible death ring, and it's getting worse. In 2025, LEO now hosts almost 10,000 active satellites, up from under 50 in 1962. But what most people don't know is that we're sending them through zones where Starfish Prime and subsequent tests injected charged particles into Earth's Van Allen belts, creating persistent artificial radiation zones that lasted for 5 years. The tests transformed Earth's electromagnetic environment into an unforeseen hazard. This is the legacy of Operation Starfish Prime, and the consequences are finally catching up to us in ways nobody predicted back in 1962. The electromagnetic weapon that never should have existed. These high-altitude tests were designed to study electromagnetic pulse effects by using nuclear detonations as powerful energy sources. That was the first thing declassified documents revealed about America's space nuclear program. Military scientists weren't trying to blow things up in the traditional sense. They were building electromagnetic field generators that happened to use nuclear explosions as their power source. The entire concept flipped conventional warfare on its head because the destructive force wasn't the heat or the blast wave anymore. It was the invisible electromagnetic energy that radiated out from the detonation point at the speed of light. Cold War physicists had stumbled onto something unprecedented. They discovered they could turn Earth's protective magnetic field into a weapon delivery system by pumping artificial radiation into specific orbital zones. The process worked like hijacking a planetary defense mechanism and redirecting it against enemy targets. Nuclear explosions in space released massive quantities of charged particles that would get captured by Earth's magnetic field lines and then transported across vast distances to predetermined locations on the planet's surface. These weren't weapons in any traditional military sense. They were electromagnetic field manipulators capable of disabling entire continental regions without firing a single conventional shot. When Starfish Prime detonated 250 miles above the Pacific, its electromagnetic pulse overwhelmed scientific instruments and disabled electronics 1,400 kilometers away in Hawaii. The charged particles from a space nuclear detonation could follow magnetic field lines from one hemisphere to another, carrying their destructive electromagnetic energy across thousands of miles of empty space before delivering their payload to enemy territory. A single bomb exploded over the Indian Ocean could theoretically cripple Soviet electronic systems on the other side of the planet. Cold War planners saw potential for EMP tests to disable guidance electronics on ICBMs in flight, introducing defensive possibilities. Soviet ICBMs relied on electronic guidance systems to navigate from launch to target, and these systems were vulnerable to electromagnetic interference. A properly positioned electromagnetic field could turn incoming nuclear missiles into expensive pieces of scrap metal falling harmlessly into the ocean. The offensive applications were even more terrifying. Scientists calculated that electromagnetic pulses generated in space could reach across entire continents through magnetic field line connections. The electromagnetic energy would travel along these invisible highways in Earth's magnetic field and emerge anywhere the field lines intersected with the planet's surface. Enemy radar installations, communication networks, power grids, and military command centers could all be disabled simultaneously without warning and without the political complications of a traditional nuclear attack. The scope of electromagnetic effects operating through magnetic field lines exceeded anything military strategists had previously imagined. Unlike conventional weapons that affected only their immediate blast radius, space nuclear detonations could project their electromagnetic influence across multiple time zones. The charged particles would spiral along magnetic field lines at incredible speeds, creating sustained electromagnetic interference that could persist for hours or even days after the initial explosion. Military leaders found themselves experimenting with planetary-scale electromagnetic warfare that treated Earth's magnetic field as a weapon system. They weren't just testing individual bombs anymore. They were testing whether they could manipulate the electromagnetic environment of the entire planet to gain strategic advantage over the Soviet Union. The implications went far beyond traditional military thinking because success would mean controlling electromagnetic spectrum dominance across multiple continents simultaneously. The strategy seemed viable because electromagnetic weapons offered several advantages over conventional nuclear missiles. They could disable enemy capabilities without creating radioactive fallout on friendly territory. They operated at light speed, making them impossible to intercept or defend against using existing technology. They could target specific types of electronic systems while leaving others relatively unaffected. Most importantly, they could be deployed without the massive infrastructure requirements of traditional nuclear delivery systems. Scientists working on the program understood they were entering uncharted territory with potentially catastrophic consequences, but they couldn't predict what those consequences might be. The electromagnetic effects they were measuring in laboratory conditions were already exceeding their theoretical calculations. When they scaled up from small test explosions to multi-megaton space detonations, the results consistently surprised them with their intensity and duration. Each test revealed new electromagnetic phenomena that their existing scientific models couldn't explain or predict. The experimental nature of the program meant that scientists were learning about electromagnetic effects in real time during actual nuclear detonations. They had no way to predict how space-based electromagnetic pulses would interact with Earth's natural magnetic field over extended time periods. They didn't understand how artificial radiation would behave when injected into the planet's radiation belts. They couldn't calculate how long electromagnetic effects would persist after the initial explosion. Military planners pushed forward with testing because the potential strategic advantages outweighed the unknown risks. Electromagnetic warfare offered the possibility of decisive victory without mutual destruction. If the United States could perfect space-based electromagnetic weapons before the Soviet Union developed countermeasures, American military superiority would be virtually guaranteed. The electromagnetic effects could disable Soviet nuclear capabilities while leaving American systems protected through geographic positioning and electromagnetic shielding. The urgency of Cold War competition drove rapid advancement from theoretical concepts to actual nuclear testing in space. Scientists had identified the basic principles of electromagnetic warfare through magnetic field manipulation, but they needed real nuclear explosions to test whether their theories would work at the massive scales required for military effectiveness. Laboratory simulations couldn't replicate the electromagnetic intensity generated by multi-megaton thermonuclear detonations in the vacuum of space. Each successful test revealed that electromagnetic effects were more powerful and more persistent than anyone had predicted. The charged particles from nuclear explosions weren't dissipating into space as expected. Instead, they were getting trapped in Earth's magnetic field and creating artificial radiation zones that continued generating electromagnetic interference long after the original explosion. Scientists realized they weren't just creating temporary electromagnetic weapons anymore. They were permanently altering Earth's electromagnetic environment in ways that would affect all future space operations, and the key to understanding how lay in the planet's own magnetic field system. Earth's magnetic shield becomes a weapon. Military physicists realized they could turn Earth's core-driven magnetic field into a weapon delivery system by hijacking the planet's natural protective mechanisms. The magnetic field that shields us from deadly solar radiation could be repurposed to carry artificial radiation from nuclear explosions to any location on Earth. Scientists weren't just exploding bombs in space anymore. They were injecting charged particles into a planetary transport network that could deliver electromagnetic destruction anywhere the magnetic field lines touched the surface. Earth's magnetic field operates like an enormous three-dimensional highway system extending thousands of miles into space. The planet's core generates these invisible roadways through the movement of liquid iron in the outer core, which acts like a massive electrical generator. The magnetic field lines flow in continuous loops from the southern hemisphere to the northern hemisphere, creating Earth's core-driven magnetic field traps charged particles in concentric Van Allen belts, now known to include artificial belts from 1962 tests. These field lines reach far beyond the atmosphere into deep space, forming a protected bubble called the magnetosphere that extends roughly 10 times the planet's diameter on the sunward side. The magnetic highway system works because charged particles from nuclear explosions follow these field lines like cars following roads. When scientists detonated nuclear weapons in space, the explosion released billions of highly energetic electrons and other charged particles. These particles couldn't travel in straight lines through the magnetic field. Instead, they got captured by the magnetic field lines and forced to spiral along the predetermined paths that connected different regions of the planet. The charged particles would travel at incredible speeds along these magnetic highways, carrying their electromagnetic energy from the explosion site to wherever the field lines intersected with Earth's surface. Military strategists discovered they could target specific locations on Earth by choosing the right detonation point in space. The magnetic field lines that passed through the Indian Ocean also passed through parts of the Soviet Union. This meant a nuclear explosion positioned correctly above the Indian Ocean would send charged particles racing along magnetic field lines directly into Soviet territory. The electromagnetic energy would travel thousands of miles through space along these invisible highways and emerge over Moscow, Leningrad, or any other city located along the same magnetic field line. Enemy electronics would be disabled by electromagnetic energy that originated from a bomb they never saw coming. The magnetic conjugate effect made this global targeting possible because magnetic field lines connect opposite hemispheres in predictable patterns. Scientists mapped these connections and discovered that every point in the northern hemisphere has a corresponding conjugate point in the southern hemisphere. Charged particles released at one conjugate point would automatically travel to the other conjugate point by following the connecting magnetic field line. This gave military planners the ability to attack any location on Earth by detonating a nuclear weapon at the corresponding conjugate point in international waters or friendly territory. Scientists plan to weaponize the same mechanisms that create the northern lights and southern lights. Aurora displays happen when charged particles from the sun get channeled down magnetic field lines and collide with atmospheric gases near the poles. Nuclear explosions in space would work exactly the same way, except the charged particles would be artificial and far more energetic than natural solar particles. Instead of creating beautiful light displays, the artificial charged particles would create devastating electromagnetic pulses when they reached the atmosphere. The concept of magnetic bottles offered even more precise targeting capabilities for space-based electromagnetic weapons. Certain configurations of magnetic field lines can trap charged particles in specific orbital zones and hold them there for extended periods. Scientists discovered they could create artificial radiation belts by injecting nuclear explosion debris into these magnetic bottle regions. The trapped particles would orbit Earth repeatedly while gradually leaking electromagnetic energy down to the surface. Researchers later found these belts persisted at destructive intensities for up to 5 years post-test. This created the possibility of sustained electromagnetic attacks that could continue for weeks or months after the initial nuclear detonation. Military planners understood that magnetic field manipulation would give them unprecedented strategic advantages over conventional nuclear weapons. Magnetic field weapons could strike targets on the opposite side of the planet without crossing international boundaries or violating airspace. They could disable enemy capabilities without creating radioactive fallout on friendly territory. They could target specific types of electronic systems while leaving others relatively unaffected. Most importantly, they operated at the speed of light, making them impossible to intercept or defend against using existing missile defense technology. Early theoretical calculations suggested that magnetic field effects might be more powerful than conventional nuclear weapon effects. The electromagnetic energy from a space nuclear explosion could travel much farther than heat or blast effects because magnetic field lines extended thousands of miles from the detonation point. This meant that a relatively small nuclear weapon exploded in the right location could potentially affect a much larger area than a much bigger nuclear weapon exploded on the ground. The magnetic field amplified and directed the electromagnetic effects in ways that concentrated the destructive energy over vast distances. Scientists expected magnetic effects to manifest in predictable ways based on their understanding of natural aurora phenomena and radiation belt behavior. They predicted that artificial charged particles would follow magnetic field lines just like natural solar particles. They calculated that electromagnetic energy would be deposited in the atmosphere at predictable conjugate locations. They estimated that the effects would dissipate over several days or weeks as the artificial charged particles gradually lost energy through collisions with atmospheric gases. Military urgency drove the progression from theoretical magnetic field weapons to actual nuclear testing in space. Cold War competition meant that American scientists needed to perfect electromagnetic warfare capabilities before Soviet scientists developed similar weapons or effective countermeasures. The strategic implications of magnetic field weapons were too significant to leave untested. But before they could attempt full-scale space detonations, military scientists needed to solve a fundamental engineering problem that would require some very unconventional thinking. Operation Hardtack's balloon bomb experiment. The challenge was getting nuclear weapons high enough to test electromagnetic effects without rockets powerful enough to reach true space altitudes. In 1958, hard-to-reach altitudes led to the Yucca balloon test, which proved high-altitude EMP can be 1,000 times stronger than ground tests. Military scientists strapped a 1.7 kiloton nuclear device to a weather balloon and floated it 85,000 feet above the Pacific Ocean. The image of America's most sophisticated weapon system dangling beneath a giant balloon captures the experimental desperation of early space nuclear testing. Operation Hardtack represented the military's first serious attempt to understand what nuclear weapons could do in the upper atmosphere. The balloon approach wasn't chosen because it was elegant or reliable. Scientists chose balloons because they had no other option for reaching the altitudes necessary to test electromagnetic pulse effects. Rockets in 1958 couldn't carry nuclear payloads to the heights required for true space testing, and aircraft couldn't fly high enough to simulate the electromagnetic conditions that military planners wanted to create above enemy territory. The experimental nature of balloon-delivered nuclear weapons becomes clear when you consider the preparation required. Military engineers conducted 76 practice balloon launches before they risked an actual nuclear device. Each practice launch tested different aspects of the balloon system, from payload delivery mechanisms to altitude control systems to detonation timing. The practice launches revealed numerous technical problems that had to be solved before anyone would trust a nuclear weapon to a weather balloon floating miles above the Pacific Ocean. Scientific uncertainty drove the extensive preparation because nobody knew what would happen when a nuclear weapon exploded at 85,000 feet. The altitude placed the detonation point above most of the atmosphere, but below the edge of space. Scientists weren't sure whether electromagnetic effects would behave like ground-level nuclear explosions or like the space-based explosions they were trying to simulate. The balloon test represented a critical proof of concept that would determine whether high-altitude electromagnetic weapons were worth pursuing with more expensive rocket delivery systems. The Yucca test launched from a U.S. aircraft carrier positioned off the coast of Bikini Atoll on April 28, 1958. The balloon carried its nuclear payload slowly upward through the atmosphere while scientists monitored its ascent from ships positioned at safe distances around the test zone. The gradual ascent gave scientific teams time to conduct final equipment checks and position their measurement instruments, but it also created hours of mounting tension as the balloon drifted higher toward the predetermined detonation altitude. Weather conditions added uncertainty to an already experimental process. High-altitude winds could push the balloon off course, potentially placing the nuclear explosion over inhabited areas instead of empty ocean. The balloon's ascent rate depended on atmospheric pressure and temperature variations that couldn't be predicted with complete accuracy. Scientists had to constantly adjust their calculations as the balloon climbed through different atmospheric layers, each with its own wind patterns and thermal characteristics. The detonation itself occurred at exactly 85,000 feet above sea level, placing the nuclear explosion in the stratosphere, where the atmosphere is thin enough to allow electromagnetic effects to propagate with minimal interference. The 1.7 kiloton yield was relatively small compared to strategic nuclear weapons, but scientists weren't testing the explosive power. They were measuring the electromagnetic pulse intensity generated by nuclear fission in the upper atmosphere. The electromagnetic measurements would determine whether high-altitude nuclear explosions could create the electromagnetic warfare effects that military strategists were hoping to achieve. Scientific instruments positioned throughout the Pacific region detected electromagnetic effects that exceeded all theoretical predictions. The high-altitude electromagnetic pulse was over 1,000 times more intense than equivalent ground-level explosions. This single measurement revolutionized military thinking about electromagnetic warfare because it proved that altitude amplified electromagnetic effects far beyond anything scientists had calculated using existing theoretical models. The electromagnetic pulse propagated through the thin upper atmosphere with almost no attenuation, creating electromagnetic field strengths that would be impossible to achieve with ground-based nuclear weapons. The intensity differential changed everything. Military planners thought they understood about nuclear weapon applications. Ground-level nuclear explosions dissipate most of their electromagnetic energy through interactions with dense atmospheric gases and surface materials. High-altitude explosions face a much less atmospheric resistance, allowing electromagnetic energy to propagate over vast distances without significant attenuation. The balloon test proved that a relatively small nuclear weapon exploded at high altitude could create electromagnetic effects comparable to much larger weapons exploded at ground level. Military leadership immediately recognized they had stumbled onto a weapon system far more powerful than conventional nuclear applications. The electromagnetic effects measured during Yucca suggested that high-altitude nuclear explosions could disable electronic systems across entire regions without creating the radioactive fallout associated with ground-level nuclear attacks. The strategic implications were enormous because electromagnetic weapons offered military advantages that conventional nuclear weapons couldn't provide. The discovery accelerated the urgency of space nuclear testing programs throughout the military establishment. Scientists realized they needed to test electromagnetic effects at even higher altitudes to determine the maximum potential of space-based electromagnetic weapons. The balloon test had proved the basic concept, but true space altitudes might produce electromagnetic effects that were orders of magnitude more powerful than the already impressive results from 85,000 feet. The electromagnetic intensity measurements from Yucca also revealed that scientists had been dramatically underestimating the power of space-based electromagnetic weapons. Theoretical calculations based on ground-level nuclear testing had failed to account for the electromagnetic amplification effects that occurred in the upper atmosphere and space. The balloon test proved electromagnetic weapons could be far more destructive than anyone had predicted, which meant that space nuclear testing needed to proceed more carefully to avoid accidentally creating electromagnetic effects that exceeded safe levels. The success of Yucca guaranteed that more powerful tests would follow as military planners pushed toward true space nuclear testing. But first, they needed rockets capable of carrying much larger nuclear payloads to much higher altitudes. The next test would escalate beyond anything they had attempted before, using a multi-megaton warhead that would create effects visible across the entire Pacific region. When Teak created a second Sunday, Teak's 3.8 megaton warhead over Johnston Island lit the sky like a second sun visible from Hawaii, an unplanned detonation above the island that demonstrated space nuclear weapons could create effects far beyond anything military planners had anticipated. The artificial daylight hung in the atmosphere for 30 minutes, while observers watched in horror from hundreds of miles away. And the thermal radiation was intense enough to give sunburns to servicemen stationed on Johnston Island who happened to be looking in the wrong direction when it happened. The Teak test represented a massive escalation from the balloon experiments that had proved high-altitude electromagnetic weapons were viable. Military engineers had moved from floating 1.7 kiloton devices on weather balloons to launching a 3.8 megaton thermonuclear warhead on top of a Redstone missile. The Redstone was America's most reliable rocket system at the time, originally designed to deliver nuclear warheads to Soviet targets during actual warfare. Using it for space nuclear testing meant that scientists were finally working with delivery systems and warhead yields that matched real military applications. Johnston Atoll provided the perfect launch site for testing weapons that might create effects visible across multiple time zones. The remote Pacific location sat roughly 800 miles southwest of Hawaii, in what military planners described as the exact middle of nowhere. The isolation meant that even catastrophic test failures wouldn't endanger civilian populations, and the vast ocean surrounding the atoll could absorb whatever electromagnetic or thermal effects the nuclear explosion might produce. Johnston Atoll had been specifically chosen as a nuclear testing facility because it was far enough from everything else to contain disasters. The Redstone missile carried its thermonuclear payload upward through the atmosphere, exactly as designed, but the guidance system malfunctioned just before the predetermined detonation point. Instead of exploding over empty ocean at a safe distance from the launch site, the 3.8 megaton warhead detonated directly above Johnston Island. The guidance failure meant that military personnel on the ground experienced the full effects of a space nuclear explosion from just a few miles away, essentially turning the test site into ground zero for electromagnetic and thermal effects that were supposed to impact only remote ocean areas. The visual spectacle of a nuclear explosion in the upper atmosphere defies normal description because nothing in human experience prepares you for seeing an artificial sun appear in the sky.